Perfect. So yeah, hello and welcome everybody to this week's seminar, which is actually part of a lecture that Pietro fortunately agreed to give on his Schumpeterian growth model. So my name is Klaus Brettner, and the recordings will also be uploaded later on my YouTube channel if you are interested, and also just be aware of that. So if you raise any questions or show your face or so on, they could end up on YouTube. So yeah, I'm very
This
happy
meeting
that
is being
Pietro
recorded.
agreed to give the seminar, this lecture. It will take place today and next week on Thursday. And he will talk about his book that he will write, and this book is about his Schumpeterian economic growth framework. But before that, for those of you who don't know Pietro, he is a professor of economics at Duke University. He is there since 1994, first as a assistant professor, then associate professor, and then full professor. Before that, he did his PhD in Yale and his undergraduate studies at Bocconi University. And he is one of the most prominent researchers in the field of economic growth, as you are well aware of, I guess. And he has many publications. I promised him not to mention all the journals, but he has published in the Journal of Monetary Economics frequently, Journal of Economic Growth, International Economic Review, Journal of International Economics, and so on and so forth. He's associate editor at the Journal of Economic Growth, co-editor at the Southern Economic Journal. And yeah, he's the founding father actually of this Schumpeterian, scale-free Schumpeterian growth framework that he will present in this week's and next week's lecture, where we will have four parts. First of all, on the basic model, then the scale effect and economic growth, then competition and economic growth, and finally multi-sector extensions of this basic model. And really, I'm very, very grateful that you agreed to give this lecture. I'm very much looking forward to it, and I just hand over to you, Pietro, and the floor is yours. Thanks a lot.
Thank you, and thanks to everybody for being here. Morning here, afternoon there, and in Japan is late evening. I think that Rio is drinking some sake to stay awake. All right, so as you probably know, endogenous growth started in the mid-80s, really broke on the scene big time in the early 90s. And there is some debate on its importance. I would argue that it's one of the most important events in macroeconomics in particular. And when we think about growth, as an undergraduate at Bocconi in the 80s, I remember that if you're interested in macro development or growth, and you ask the professor for a formal model, you would get Solo. That was the only thing available. So it was a big change when Romer made his breakthrough, both in 86 and with the 86 paper and the 1990 paper. And I was in graduate school between 1990 and 94, and there was excitement. Everybody was doing growth. It was a big wave of production, and many issues were identified, some resolved, and some are still being debated. So that's the intellectual background, and you can understand why 30 years later I'm still excited about working on these topics. It has been a really big change in the way economists can inform the debate on development, macro development, and growth. Now, the excitement of the 90s, in fact, produced lots of work, much of it good, some of it didn't make a mark. But then with developments in theory and development on the empirical front, there was another acceleration in the production and another sort of a mini revolution at the turn of the millennium with the unified growth theory and all of the other stuff that Daron and others have done on institutions. So the field exploded. It went through a second big bang, so to speak. And the field now is I know, orders of magnitude larger than it was when I was your age. I'm looking at the faces of the young people here on the screen. Okay, so that's the background. What did I do specifically? Well, as a graduate student, I paid attention in class when Xavier Saleh-Martin introduced us to the Romer model, in particular the Grossman-Helpan variant of variety growth from their 1991 book. A really exciting book to read at the time. Then I remember he introduced us to this notion of creative destruction, told me, go and read Agion Howitt. I read again Howitt, and I had a background for my undergraduate dissertation on the Schumpeterian hypothesis, market structure, and innovation. And it struck me immediately that the theory that all these people were developing potentially could be IO based, could use a lot of, it did use insights from IO, but not, they were not making it very explicit. And bringing more IO kind of thinking and the empirical facts that we learned from the debate on the Schumpeterian hypothesis would probably help us write better models and expand the scope of the theory. So I got busy and I started working on these things. So what I'm going to show you is a very simple model, so simple that it has an analytical solution that provides the basis on which one can construct many applications. One thing that I had in mind when I started working on these things back then was the model has to be tractable. The IO foundations have to be transparent and consistent with the evidence. And it turns out that the model is very flexible because it has many applications. So in this set of lectures, I will not be able to show you how many applications one can do with it, how many things one can do with this model. But as I go along, I'll try to give you a hint about the scope of the approach. And if you're interested in any details, you can look at my webpage, and then hopefully soon I will have the draft of the book I'm writing available there. All right, so that's it, so that we're all on the same page. And so let's talk about the model, and I will, as I go along, I will try to give you more perspective that I could fit in the slides. So we want to think about a world. This is a macro model. So we want to think about a world with an economy with a household sector and a production sector. For now, I will abstract from the government, but there is a lot of stuff concerning the government, taxation, public R&D, and other things that the provision of public goods that one can do with these models. But let's keep it simple. So standard growth model with the household component and the production component. I'm going to stay within the beaten path of standard macro when I describe the household. So this is a model that is entirely about the production sector. And the production sector is Schumpeterian in the sense that the key activity undertaken by this part of the economy is innovation. So for simplicity, the model will be a model, knowledge-based model, no physical capital. The input that we allocate across different activities is labor. This is the simplification that people like Grossman, Helpan, and others introduced in the early 90s and proved to be extremely powerful by stripping out of the model a lot of ingredients that are not necessary to obtain the key results. And that makes the models extremely tractable. So the households consume, save, and supply labor. We are going to go with an elastic labor supply for most of these lectures. There are in the published literature many applications where the models have been extended to endogenous labor supply and unemployment. So that margin can be introduced, but we are not going to do it here. So I'm going to refer to these units called firms. This is the key institution that I want to study in these models. My interest in this field was already pretty high when I saw models that claim to have firms, Romer, Grossman, Helpan, and I couldn't recognize firms in those models. That increased my interest in the literature in this approach, because I told myself, okay, there is room for improvement here for somebody that comes from IO. Let's think more seriously about these units called firms. So differently from and I think that this is the main contribution of this approach, differently from the early models in which you had models of variety expansion, where innovation is bringing a new good to market, And once the new firm that brings the new good to market is in operation, the firm doesn't do anything else. The alternative was models of creative destruction like John Howitt, where new goods are brought to market by new firms that replace existing firms in this vertical characterization of technology as opposed to the horizontal characterization of technology of variety expansion models. And in that approach, once the new firm captures the market, does nothing, does not innovate, sits there and waits to be killed by the next challenger. So for a very long time, people thought that these were just two ways of telling the same story. But if you come from the literature that I was raised on as an undergraduate on the Schumpeterian hypothesis, you recognize immediately that in fact, the variety expansion model is talking about extensive margin, entry of new firms in the market, and the creative destruction model is talking about a particular mode of innovation that Schumpeter described in some of his works in words that has to do with the vertical dimension of technology, what should happen within the firm. So if you imagine a variant like Federico Aitro's variant of the creative destruction model, in which innovation is done by the incumbents, you see that those literature essentially were coming at the problem of market structure innovation from different angles, but didn't go all the way to realize that the two dimensions of innovations are in fact complementary. This will emerge as we go through the equations of the model. So for me, there is a foundational moment, the foundation of the firm. A firm is founded only once at a point in time. We call it entrant at that particular point in time, and then we call it an incumbent. So a foundation, firms develop new goods and set up operations to serve the market. So we call this variety innovation or entry. One of the activities that, one of the names that these activities get in some of the literature is entrepreneurship. There are a bunch of words that are relating to these things. Now, the important thing is that after the foundation, the firm becomes an incumbent. So it's in operation. And in operation, what do firms do? They produce, they sell, and in this scheme, they do in-house R&D. This is the key innovation relative to the models from the 90s. Incumbents do innovate. And the models can be written in terms of cost reduction, quality innovation, both in some specification. So we're going to go with the cost reduction view of the world in this set of lectures, but everything I do here can be done in terms of quality innovation. All right, so that's a background. Now we're ready to go to the equations. This is my household. There is a representative household that with a mass of members, all identical, and the size of the household grows at rate lambda. That's also the growth rate of the population in these very simple environments. Now you might notice that differently from what you might see in most of the literature, I do not set the initial value of the population at 1. Why? Because in this theory, based on increasing returns, scale matter. So arbitrarily setting equal to 1, a parameter lambda, capital lambda, that is the initial value of the population, arbitrarily set that capital lambda equal to 1 removes from the model something that encodes normalization, that removal, but in fact is removing something from the model that must play an important role because the model is based on increasing returns to scale. So then the household has log utility. For simplicity, you can write these theories with the standard CIS, but it adds very little to the insight. And so utility is logging consumption. My notation is a little bit different from the standard textbook, so let me go through it. The variable that plays a key role in this model is consumption expenditure by this household that I denote by Y. The price index of the consumption good that these guys buy is PG. And as again, L is the size of the household. So consumption per capita is expenditure divided by the price of the good that they buy multiplied by the size of the population. And then I have the budget constraint of the household, not in per capita, but in aggregate terms. So A dot is the change in household wealth, that's savings of this savings. And the household has two forms of income, asset income, R times A, and labor inc of W times L. And then there is expenditure. So that's the notation. And notice here that I don't force population growth to be positive. These class of models, because they are scale invariant, accommodate very easily negative population growth. Scale invariance means the growth becomes independent of the rate of population growth, not just the magnitude, but also the sign. So contrary to some habits that come from reading the early papers of the 90s, we don't need to take a stand on whether population growth is positive or negative. This theory accommodates negative population growth. Okay, so what do we get from the household? Because it is so simple, we get a saving rule. Here in the US, we call it the Euler equation. In Europe, oftentimes you guys call it the Keynes-Ramsey rule. Bottom line, that's the behavior, the saving behavior. And I like to interpret it in terms of the reservation rate on rate of return on assets that the household demands in order to be willing to save. And this is the standard equation that we are all familiar with. And labor supply is inelastic, equals to the population side. Again, remember that it's very easy to move to an environment with endogenous labor supply. So now we go to the production side of the economy, where most of the interesting action takes place. So there is a final good that is a representative producer supplies this final good homogeneous, and this good is produced with this CS technology that has two important features. There is an elasticity substitution, so intermediate goods used to produce these final goods are imperfect substitutes, and there is a law of variety effect, the parameter chi. And again, this is very familiar from the models from the 90s, Romer, Grossman-Helpan, et cetera, et cetera. So the important thing is that profit maximization by the competitive producer using this technology gives us the demand system that is in the second equation on the slide. And by now we're all familiar with this. The firm sells in proportion to total consumption expenditure. That's the measure of the size of the market in this class of models. And then there is a function that has a numerator, the price of the good sold by this firm raised to minus epsilon, and then something that maps into the price index associated to the production function at the top. Now, in order to understand how this theory works, it's very useful to write that demand system in terms of the firm's revenue. And then if you are an IO guy, you recognize immediately pretty much the foundations of how we think when we think about an industry. The firm's revenue are market size times the market share. So the market share is a function of homogeneity of degree zero in all the prices. And a lot of the action in this class of models is coming from this object over here. People are used to think in terms of standard monopolistic competition with atomistic firms, which is the model that we're writing here. And in that case, then we always say the denominator is taken as given. So the demand system is actually giving us a collection of isoelastic demand functions, and that makes your life very easy. Now, the very fact that the firm's revenue can be written as a function of market share, that is a function of all the prices, should remind us or alert some of us to the fact that in fact these models can be easily extended to endogenous markups. All you need to do is to change the environment from an integral, where firms are atomistic, to something like a summation. So the firms are non-atomistic. The modern day word is granular. And then you allow firms to take into account the presence of their price as the denominator. We are going to do this next week, models of this class next week. But that's essentially the specification of this theory that I wrote down in my PhD dissertation and in my early publications. Early on, I wrote models with endogenous markups. Later, I simplified the models by going to constant markups for marketing reasons. But essentially, this is the core of the theory from in terms of the demand system that drives everything. Okay? All right. So now we have the description of the demand system faced by intermediate producers. We can talk about intermediate producers. These are the key Schumpeterian agents in this class of models. The two key Schumpeterian agents in these models are existing firms, they innovate in-house, and entrepreneurs that set up new firms. So let's talk about the existing firms. For simplicity, we are going to go with a model where there is one firm, one product. This is not an assumption. It's a result depending on how you set up the environment. It's very easy to extend models of this type to multi-product firms. I'm working on a paper of that type with Antonio. So depending on how you set up your primitives, your demand system, your technology primitives, et cetera, you can obtain that in equilibrium firms supply only one product or the firms supply multiple products. I tend to think of the best way to interpret a one product, one firm model is to say that there are very high coordination costs from trying to form a multi-product firms. And that has been formalized in the literature. I think Antonio is one of the early papers from almost 20 years ago of endogenous growth models of this type with multi-product firms. And he and I are revisiting the issue now that we are older and wiser. Okay, so the production technology, the first equation at the top there says that the firm produces with labor only. And there is a TFP term, which is the firm specific knowledge, ZI. That's going to be the key state variable of these theories, raised to some power theta. Theta is a parameter of technological opportunity, various names in the literature. Okay, so important thing is that output is produced by multiplying variable labor you multiply variable labor by TFP. Variable labor is the difference between the total production labor employed by the firm, that's L sub X, and then you subtract overhead labor. So the important thing is that these firms produce with a fixed operating cost. That fixed operating cost makes an enormous difference in how you think about endogenous growth models. With that fixed operating cost, I'm going to anticipate now one of the key results that we're going to find later. With that fixed operating cost, variety expansion cannot be an engine of growth. Why? Because every time you set up a new firm, you replicate the fixed operating cost, which is in units of labor. So you put pressure on the economy's labor supply. This is an insight that is old. This has been understood by some almost immediately concerning variety expansion growth models, but most of the time it emerges, in my experience, in private conversations, not necessarily over a beer of wine, but say brainstorming in somebody's office, a visitor comes from a seminar, you discuss things, what's the key assumption driving everything in Rome? And I remember people, myself and other people agreeing in my own office when I was a junior professor saying, yeah, the fact that it doesn't have a fixed operating cost is very important. And later on, I will show you exactly formally why this is the case. So that fixed operating cost plays a very important role. In fact, plays two roles. Number one, it gives us static economies of scale at the firm level. And so that's another source of increasing returns to scale in this theory. And that's something that we should take very seriously. Because ultimately, when we go to the data, we want to think about firm size, the role of firm size, and things like that. And that depends a lot on an object like that fixed operating cost. Okay, then the other thing is that this firm innovates. So there is an accumulation technology, firm specific, that is basically taken from the early models of the 90s. That says that the addition to the knowledge stock, firm specific knowledge stock of this firm is proportional to the amount of labor that this firm allocates to this activity called R&D. I like to think of these, I call them R&D for short, but in general, these are learning activities. It doesn't need to be formal R&D in a lab. It can be a firm in some developing country that allocates a fraction of its management time to figuring out what the competitors are doing or learning from frontier countries that have more advanced technologies, okay? So in general, I like to think of this labor as allocated to learning. Adoption of technology is a form of learning, and so that it's allowed in this scheme. So, but for short, I'm going to call it R&D labor. Okay, so the factor of proportionality is a constant alpha, and then this K term that denotes spillovers, knowledge in the public domain available to this firm. And this is where things get interesting in this kind of theory, because often some misconceptions concerning this kind of theory arise from how one thinks about these knowledge spillovers. Now, the tradition is to call these knowledge spillovers, but strictly speaking, is a diffusion process. The fundamental idea of endogenous growth theory, and Romer himself has insisted on this point, although not with success, is that his theory is entirely about knowledge, ideas, and the point is that ideas are created locally, but because they are no rival, they can be used globally. With that, I mean that ideas are generated by specific individual units as the output of some activity, potentially as the byproduct of another activity, right? Like in Romer 86, where knowledge accumulation is the byproduct of capital accumulation. But the important thing is that ideas are generated locally by these kind of activities, but because they are not rival and only partially excludable, second part is very important, then can be used simultaneously by multiple parties. And that is recognized as the key source of increasing returns to scale in models of endogenous growth. So how we model this operator is very important. So here in this approach, I'm going to follow what we did in a paper with Charles Mulders that we published in the Economic Journal in 2002. That paper has a very general framework that microfounds the spillover function. And what I'm going to do here is use the insight coming from the paper to think about the spillover function as some integral over the firm-specific knowledge across all the firms in the market. There are n firms in the market at a point in time. All of them have their own knowledge stock. So what is the stock of spillovers available to firm I? Well, is the weighted integral of the knowledge produced, accumulated up to today by all the firms in the market. And the weight is some function that we can specify according to taste as a function of multiple inputs or other things, much complicated objects. But here we're going to go with the simplest possible specification, which is we take the weight D, we make it a function of the number of firms, and we make it a decreasing function of the number of firms to capture the notion that as the number of firms that sell differentiated goods expands, these firms become, on average, more and more distant from each other in technology space. And that reduces the scope from learning from each other. Okay? And for simplicity, then we make the weight 1 over n. Later on, I'm going to show you models where D of n can have a more interesting and rich form, but this is the simplest specification possible. Now that transforms this operator into an arithmetic average. Some people have latched on to the property to criticize the theory, but in fact, that's just a special case of much larger family of operators that one can use. Okay, so that's a conceptual foundation of what we do here. The important thing is that despite the fact that K has a subscript I, we take it because, again, firm I is atomistic and this is an integral. We take K as beyond the control of the individual firm. Later on, I'm going to show you models where firms take into account the presence of their own knowledge in this operator K, similar to the concept of endogenous markups that I described before, and that gives rise to more interesting models of, again, using the modern word, the word that the modern literature uses to denote these things, granular firms that are not atomistic, and internalize a bunch of things that we don't internalize when we do monopolistic competition. All right, so now we can speed up a little bit because I described pretty much the conceptual foundations. The rest should be clear as we go along. All right, so given these two technologies that the firm operates, production technology and R&D technology, what does the firm do? Well, the firm maximizes the present discounted value of the dividends, maximizes shareholders' value. That's a strong statement. I have a thriving research agenda. Among the applications of this approach, I have a thriving research agenda with friends like Maurizio, Raul, Domenico Ferraro, in which we introduce corporate governance issues, separation of ownership and control, and we study the behavior of these models when whoever is in charge of the firm does not maximize shareholder value. So we create a principal agent problem, a conflict of interest between management and shareholders. And that's a very interesting aspect of this theory, that it can be done in a very, very tractable manner. All right, so, but here we go with the simple assumption that they maximize shareholder value. What's the dividend flow? Dividend flow is the difference between, is the quantity produced times the difference between the price and the variable unit cost of production. That given our technology linear in labor, this is linear in labor, then we get simply that expression there. Then we subtract the fixed expenditure on overhead labor, and then we subtract expenditure on R&D labor. And then we also have a death shock. There is some exogenous probability the firm dies according to a Poisson process. That is not a necessary ingredient of the theory, but it's an element that simplifies the analysis in some cases, because it gives us that in a neighborhood the steady state dynamics is symmetric. I'll come to that in a couple of slides. All right, so that's what firms do. They choose a time path of the price and of R&D labor. Those are the two control variables, subject to the technological constraints that I described before, to maximize shareholder values. So the operation then gives us the maximized value of the firm. What do I mean by maximized value of the firm? The word maximize is there to denote, to emphasize the fact that entrants anticipate that after entry, once in operation, they behave like incumbents, and they solve the maximization problem that I described here. So the maximized value of the firm is the object that enters in the calculation that agents in the economy do when they decide whether to invest resources in setting up a new firm. That's a free entry condition that drives all of endogenous growth in the early models. Romer, Aghion-Howitt, that's how they solve for the equilibrium, free entry condition. So to do that, I need to specify an entry cost. So I'm going to say that there is an entry cost, an expenditure on an entry, beta y divided by n, that translates into an expenditure on labor employed in entry. And there are various ways of interpreting this. I'm not going to go through the details here. I have published papers where we discuss at length what the specification of the entry cost really means. For macro, that translates into there must be some entry technology that has the property that the gross change in the number of firms is the labor allocated by aggregate labor allocated by the economy to this activity called entry times some inverse of the labor requirement per entrant. Okay? And then we can quibble on how to interpret this term, but that simply translates into this expenditure on entry thing. Now, why did I call this the gross entry? Because in fact there is a depreciation rate of this form of capital present in this model, because firms die at rate delta. So if I write the net entry rate, I need to subtract delta n from this expression. And in solving the model, we do that. All right, so that's a setup. So the important thing is that this setup gives us the notion that there is this part, there is a free entry condition, and L sub n, employment in this activity that we're calling entry in this economy, is positive if and only if the free entry condition holds. So the equilibrium, as we know from Romer, Grossman, Hellman, all the founding fathers of the field, there is an equilibrium very well defined that has no entry, which is Ln, employment in entry, equal to 0, and that holds when VI is less than the cost. The maximized value of the firm is less than the cost of entry. Now, these no entry equilibria, no innovation equilibria, are typically ignored in the literature, but in fact, we are going to take them very seriously, because that is where the model becomes we see how the model is extremely tractable and powerful. By the way, this corner solution of 0 employment in entry shows up also in the problem of the firm, because the problem of the firm is linear in labor employed in in-house innovation. And there is a non-negativity constraint on LZI as well. So the problem of the firm also features a corner solution where if the benefit that I get from allocating the marginal unit of labor or innovation is less than the cost, and the marginal cost is W, then direct monetary cost is W, then I don't allocate labor. Okay, so we're going to take these corner solutions very seriously, and I'm going to show you exactly how as we go along. All right, so the important thing about in this model, if I initialize all the firms with the same stock of knowledge at the beginning of time, then the model, as an industry model, IO model, is fully symmetric, treats firms completely symmetrically. So firms are going to make identical decisions. They're going to charge the same price, invest in R&D the same amount, and grow at the same rate. So the symmetry is preserved throughout the transition path. In particular, if then, as we're going to do, we assume that entrants join the industry with their initial knowledge equal to the industry average. Okay, so this is just a way of compressing the firm size distribution of these models to something degenerate. Symmetric equilibrium is just a degenerate firm size distribution where everybody gets market share 1 over n. These models can be extended to asymmetric firms. Filippo has one of the best papers on how to do that. And in the book that I'm hoping to put online soon, I have a few chapters that explain how this works. So I don't see the symmetry of the equilibrium as a weakness of the model. I actually see it as a strength because it allows us to study the dynamics of these models with scalars as state variables instead of functions describing the non-degenerate first size distribution. I'll say more about this as we go along. All right, so this equilibrium is symmetric. We only need a condition, which is 1 larger than theta times epsilon minus 1. Let's understand the condition. What is theta? Theta is the elasticity of TFP with respect to firm knowledge. What is epsilon? The price elasticity of demand, a measure of the steepness of the demand curve faced by individual firms. Remember, what do these firms do? These firms allocate labor to figuring out how to reduce production cost. That because they charge a constant markup over their marginal cost of production, that allows them to reduce price and potentially steal market share from the rest of the industry. That is the beating heart of the Schumpeterian models, competition for the market share. So theta times epsilon minus 1 is a measure of the curvature of the revenue function of the firm, or better, of the market share of the function of the firm with respect to its own knowledge. Okay, so that this assumption is sufficient to guarantee that no firm tries to take over the entire economy. That's what the condition is doing there, is justifying the focus on a symmetric equilibrium by telling us, look, in this economy, each firm faces an incentive to try to expand that is decreasing in its relative size. And therefore, this is not a natural monopoly model. It is a model that naturally accommodates multiple firms doing innovation and growing at the same rate in steady state, in some kind of stationary state. And I have chapters in the book that formally explain this process and formalize this concept. I think that this is a strong point of these models because in the current literature, there are lots of papers that claim to have non-degenerate firm size distribution that are stationary. But in fact, if you look under the hood at the core of the model, there is a structural technology that in principle would allow a firm to take over the entire economy. And then there are special assumptions on the entry process that give us a stationary distribution of firm size. None of that is needed here. To my knowledge, Filippo's paper is the only one that has this property. All right, so then once we have this symmetric equilibrium, we solve for the fair demand for production labor, given by this expression that you probably recognize from many, many papers that you have read in your studies. And then we have the entire structure can be represented in terms of two rates of return to these two forms of investment that take place in this economy. The first equation is the rate of return to accumulating knowledge inside existing firms. So the rate of return to in-house innovation. I'm going to call it firm innovation for short for the rest of the lectures. What we notice here is this rate of return is linear in the size of the market. Why? Remember what is Y? Y is total expenditure on consumption that induces expenditure of intermediate goods. So Y gives us a measure of the size of the market for intermediate goods, the market for which these guys are fighting. And this rate of return is also linear in the market share of the firm, 1 over n. So that's the n at the denominator here. Okay, so those are the two key components that these models track in the IO sense: market size, market share. And then there is the wage. This is the expenditure on R&D. This term, the growth of the wage, reflects the fact that that's a capital gain associated to the shadow price value of knowledge that comes from the maximization problem of the firm. It's a standard element in all of endogenous growth theory. And it represents the fact that when the wage increases, the cost of producing knowledge increases. And in the equilibrium when firms do innovation, that shows up as a capital gain loss term in the asset pricing equation that gives us the rate of return to innovation, to firm innovation. Second equation is the same concept, but applied to the entry process. This is simply the rate of return to owning equity in an existing firm, or equivalently in this model, in free entry equilibrium, in setting up a new firm. And this rate of return, asset pricing theory tells us, is the dividend price ratio plus capital gains losses. This term over here, the first part is the dividend price ratio. The second part is the capital gain losses. Remember the free entry condition. The free entry condition says that when there is entry, V, the value of the firm, which is the price, the asset that we're pricing here, then V is equal to beta Y divided by N, and that gives essentially the capital gain loss term. Again, I want to attract your attention to the fact that the rate of to entry is a very simple function of market size and market share. Okay? And then there are these other terms that essentially are the same things. So this is a very, very simple structure. And I want also you to notice the presence of this minus delta term, which is the exit shock of the firm that applies to both rates of return. So that's a structure. From now on, we can do macro. I spend more time than usual on these slides to make sure that you guys, that you understand, you have a good understanding of the micro foundations of the theory. All right. So how do we define a general equilibrium Fourier's economy? This is where my approach differs from many of the papers in the literature. I realized early on that models are much clearer if we are explicit about the equilibrium concept. For me, the equilibrium concept is no arbitrage. So this is an economy in which there are multiple assets. You can, and we are pricing those assets according to these two rates of return equation. Remember, those are asset pricing equations. So no arbitrage says that returns have to be equalized. And if they're not, then some activity is return dominated and therefore doesn't take place. Those, in fact, are the two corner solutions that I described conceptually before. What happens if RZ is less than RN? Then RZ, investment internal in-house, is return dominated and firms don't innovate. That's essentially all of endogenous growth theory prior to this approach, because firms in those models do not innovate. This theory is telling us that those models have features that give us a return to investment internal to the firm that is less than the return on alternative forms of investment, or even more importantly, less than the reservation rate of return of households. And then we have the same thing. What happens if Rn is less than Rz? Then entry is return dominated. And so there is no incentive to add new firms to the market trying to fight for the market share. And the only thing that takes place in that economy would be vertical innovation. So through this no arbitrage concept and this corner solutions, the model nests. As special cases, the seminal models of endogenous growth of vertical and horizontal innovation. The key no arbitrage relationship is with respect to the reservation interest rate of the household, because it's possible, in fact, there is in the model, there is an equilibrium in which both RZ and Rn are less than Ra, so households are not willing to save, not willing to sacrifice current consumption, and therefore there is no innovation of any type in the economy. And this is important in trying to understand the secular evolution of economy from an equilibrium with stagnation to equilibrium with innovation. All right, now that's a no arbitrage argument of rates of return, but the asset market equilibrium requires also another condition, that the value of the household's portfolio equals the value of the securities issued by firms. That translates into the claim that A, household wealth, is equal to N times V in my symmetric equilibrium. What is the value of securities? V per firm, then I multiply by the number of firms, and this is basically the aggregate value of the stock market in this economy, and that is the household wealth, because in this economy, the only security available to households to save is equity in intermediate firms. Okay, so that's an intuitive understanding of that. So we're doing general equilibrium. I'm free to choose a numeraire good. We're going to choose labor as the numeraire, and so we set the wage equal to 1. So from now on, the units of this model are, when you look at the price, that price is telling you how much I have to work to acquire this good, because all prices are measured in units of labor. Okay, which I think is a natural way to think about growth, because growth is about us becoming more and more able to purchase goods, given the effort that we put in generating income with our labor. All right, so the zone of inaction, I discussed those. There are two for Ln and Lz. The zone of inaction for entry basically tells us that this economy has two configurations. The free entry configuration, where A is equal to NV, which then is equal to beta times Y, given the free entry condition and our characterization of entry costs. That is going to give us constant expenditure per capita and constant interest rate. That's great. That configuration gives an extremely simple specification of the model, and I'll show you why. But then there is a possibility that free entry doesn't hold. So A equals N times V, that must hold all the time, but now N times V is less than beta times Y. In this case, Y and R are not constant. Things get a little bit more complicated, but still tractable enough that we can solve for the equilibrium. So let's understand configuration 1 first, the free entry, because this is the most popular one. I myself, in my career, I've published, most of my papers published early on, study only the free entry configuration of these models. Later, I started studying also the other configurations as I became more ambitious in what I wanted to accomplish. So the important thing is this. The free entry condition, in fact, is telling us the wealth is proportional to consumption expenditure. Or better, consumption expenditure is proportional to wealth. Fantastic. If you remember the derivation of the Friedman consumption function from your studies of Macro 101, you see that that's an extremely convenient result that can be fully rationalized in terms of standard macro. But the important thing is that if I substitute that result into the household budget constraint, and I use the Euler equation that comes from log utility, the budget constraint of the household becomes this expression over here. You can see immediately that the growth of consumption expenditure on the left and the right of the equality cancels out. And so this equation gives me immediately a solution for expenditure per capita. And the rule, this consumption rule, says expenditure per capita is proportional to the wage, to wage income per capita. Remember that W is normalized to 1, and therefore consumption expenditure per capita, consumption expenditure per capita is constant. That immediately through the Euler equation also gives me a constant interest rate. That's where it comes from. No tricks, no magic, straightforward application of macro principles. Now, what happens in configuration 2? The key is that wealth is not proportional to Y. So we need to be a little bit more subtle here, but going through the derivation, I think reveals a lot about how macroeconomics works. So we decompose A dot in the sum of these two terms, changing the mass of firms times asset price per firm plus mass of firms times change in the asset price of each firm. And then we realize that asset income, R times A, is in fact the rate of return to equity. I have already made the substitution here. And this is an equilibrium where there is no innovation of any type. So firms are not investing in-house. So in parentheses here, you have the rate of return to equity multiplied by the size of the portfolio. Now, again, because nobody's investing in entry, then the evolution of the number of firms is simply, it shrinks at some rate delta. V dot cancels out from the left and the right. And so what happens is that the budget constraint collapses to an expenditure rule that says expenditure per capita is some function of, in this case, the profitability of the existing firms. And that's why we get phi, the fixed operating cost, multiplied by the number of firms divided by population size, which is the number, the mass of firms per capita. Okay? And then, because I have this expenditure rule, I obtain an expression for the interest rate. What I wanted to point out here is that these are two functions that tell me that in these two configurations, I have expenditure as a function of the state variables of the model, and the interest rate is function of the state variables of the model. In particular, if I choose n over L as a state variable, then this becomes an extremely simple structure that I can play with. And that's exactly what we will do. Okay? So using the information, then remember the population grows exogenously. So in order to work with a stationary variable, we choose to work with the number of firms per capita. And then in an equilibrium with free entry, remember that in equilibrium with free entry, expenditure per capita and the interest rate are constant. So I can go and solve the equation for the rate of return to firm innovation. And because R is constant there, expenditure is constant, I can solve that equation for the equilibrium growth rate of knowledge of the firm. I'm going to call this the rate of firm growth as a function of the state variable of the system. Okay? So if you want to call this some sort of firm investment function, that's fine with me. Important thing is that I get the growth rate, firm growth as a function of the state variable. Then I do the same operation on the rate of return to entry. Now, remember the corner solution on LZ. That means the firm growth has two branches. One that holds when firms invest, the top, and one that holds trivially zero when firms don't invest. Okay? Now, that tells me that if I go and use the rate of return to the creation of new firms or to equity in this model, then I'm going to get three branches. The first branch is when there is no innovation of any type. Then the number of firms per capita is shrinking at rate delta plus lambda. Then I have a branch where there is gross investment in entry, L sub n is positive, but incumbent firms don't invest. Okay? Then that equation gives me that the rate of entry or the growth rate of the number of firms per capita is a function of the number of firms per capita itself. Okay? And then I get another branch where I account for the fact that firms are innovating, but still that becomes a function, tells me that the growth rate of the number of firms per capita is a function of the number of firms per capita. So I want you to see that this is a piecewise differential equation. This is a one-dimensional system. The differential equation is piecewise. N dot over n is only a function of n. The other thing that I want you to notice is that on the right-hand side, I have linear functions. Okay? And that is the key to the simplification. Now, of course, the corner solutions are going to give me thresholds of the state variable that partition the state space into three regions where each one of these branches hold. Okay? So this equation is the general equilibrium dynamics of my model. The entire general equilibrium structure of the model reduces to a single differential equation in a single variable, piecewise linear on the right-hand side. Doesn't get any simpler than this. All right, and then I have the expressions for the thresholds there. So there are conditions under which this system converges to some steady state in the top region, because I'm interested in working with parameters that give me convergence to an equilibrium with growth. So I want this system to go from the initial condition to a steady state in the region that gives me the top branch. And these are the restrictions, the parameters that I need for that to happen. And this is the phase diagram. Okay, this is how simple this model is. Given initial condition, say here, then the economy follows this path. Remember, the n is a predetermined state variable. So given initial condition, the system is stable, then in value is negative in this neighborhood. The system then moves to the left, rises, and then converges to n star. And n star is what I call the scale invariant endogenous growth steady state. Now, let me tell you a word about this gray region. Remember, there are fixed operating costs. So if there are too many firms in the market share is too small, firms can be making losses. So this is the negative profit region. In that case, standard economic reasoning tells us, okay, then some firms will leave, and enough firms will leave until the surviving firms have positive gross profit. They can cover the fixed operating cost. So the firm is never inside the gray region. So the range of admissible values for the mass of firm per capita is from 0 to n max, which is the point where firms make their negative profits. So that's my state space, that's my phase diagram. All right, but there is more. So before I go there, let me characterize a little bit the steady state.
Sorry.
Yes, go ahead.
With no fixed cost, the number that could be supported could go to infinity or will just shift to the right. Okay.
No, correct. If phi is equal to 0, I get Romer. Or better, Grossman-Helpman 1990.
I see. Thanks.
If phi is equal to 0, two things happen. N grows forever, so the movement is to the right, because in fact, N, the mass of firms, grows faster than the population. So the economy leaves this region, incumbents stop doing R&D, and then I get explosion toward the right. That's essentially variety expansion from the 90s. That's the sense in which that model is nested in this one. Okay?
Yes, thanks.
I'll come back to this point. It's an excellent question. All right, so let me characterize a little bit this steady state. So we have a condition. We want the steady state to be to the left of the threshold NZ. Remember that we have an explicit expression for this threshold NZ. Here it is. We have a solution for n star, because if I set n dot equal to 0 in the top branch of this equation, I get my n star. So I can do one line of algebra. And I get that this condition, restriction on the parameters that I call the endogenous growth condition, must hold for my system to converge according to this phase diagram to that steady state, scale invariant endogenous growth steady state. Okay? That endogenous growth steady state has two things going on. Number one, there is continuous entry of firms. The fact that the number of firms per capita is constant means that the number of firms is growing at the rate of the population. All right? So Romer is in there, but it's Romer constrained by the fixed operating cost. So that the number of firms cannot grow faster than the population. The other thing is that firms are innovating. And that dimension of vertical innovation is unconstrained by the labor supply. So that's why along that margin, this model delivers endogenous growth. And the important thing is that when we look at the determination of n star, the number of firms per capita, it's proportional to expenditure per capita. What it means is that the number of firms is going to be proportional to aggregate expenditure. Remember what aggregate expenditure is, the size of the market. So this steady state has the property that the number of firms is proportional to the size of the market. That explains the scale invariance. Because when I take the solution for the number of firms and I substitute it into the equation for z hat, this equation here in this branch, okay, in this branch, then I get that the rate of firm growth is independent of parameters that of things that relate to the scale of the economy. That's the sense in which growth is scale invariant. Z hat star, the growth rate of knowledge at the firm level, does not depend on the size of the population. And so it's independent of the parameter lambda that scales the population up and down. It's independent of the growth rate of the population. And why does this happen? Because the number of firms adjusts to market size, Y, capital Y, which is proportional, which is L, population size, times expenditure per capita. So the reason why this model sterilizes the strong scale effect, it's because it sterilizes the market size effect. Okay? That's the sense in the notion of scale invariance here. Okay, so I told you that the system is actually even simpler than it looks here. And the key is that on the right-hand side of the n dot equation, I have linear expressions. Some of you might have already recognized that if I take the top branch of that equation, either of the two branches, but let's focus on the top branch. So let's focus on the region n less than nz, so a region where there is possibly endogenous innovation. Then that's the differential equation representing motion of my state variable in the branch. Some of you might have already recognized this equation, either because some of you have, I don't know, run into papers or books that talk about logistic growth, or because some of you are good at math and they were told that this is a Bernoulli equation. I have co-authors that study with the great Giancarlo Gandolfo in Italy, and they knew these things inside out. What am I getting at? That equation has an explicit solution. So I like to interpret in terms of logistic growth because it really makes sense in this environment. So what is new? New is this composite parameter. New gives me what is called the growth coefficient or the intrinsic growth of a particular species. So this equation is inviting us to think about firms as a species that proliferates, grows in mass in a confined environment, subject to some carrying capacity constraint. So nu is the growth coefficient, and this term over here is what is called the crowding coefficient, which is also related to the carrying capacity. N star itself, in fact, is the carrying capacity. So I can rewrite that equation in this form, and then many of you will recognize it immediately. Yeah, that's a logistic equation that I saw in undergraduate classes in, I don't know, biology, economic diffusion, or technological diffusion, or things of that sort. And the logic of the model is precisely that. The math is describing the proliferation of a species called firms in a confined environment that has a finite carrying capacity. And so there is a crowding coefficient, in this case, linear crowding. That means the growth is logistic. The mass of firms cannot grow forever, must follow a bounded path, in particular, in some cases, S-shaped. That's a very interesting property of these things. But the important thing is that the equation has an explicit solution for n as a function of time. Okay, that's how simple this model is. This entire class of models is. We have the explicit solution. So we call n star the carrying capacity, and then the equation is describing the path through which these species, firms, converge to the carrying capacity from any initial condition. All right, good. So now we're going to play with that property to generate more interesting. Yeah, I'm good on time. Now we're going to play with the property to do interesting economics. So this is a knowledge-based model. There is one factor of production called labor that is used in all activities. So what is GDP in this economy? Well, it's the production of the final good, which in equilibrium is equal to consumption expenditure. So GDP is Y equals G. Okay, that comes from that function that I showed you earlier. Important thing, remember that there is a price index for this consumption good in this economy, and this is the formal expression for the price index. And this price index, remember, every production function of the CS type has associated to it a price index of the CS type. So That's my price index. So in GDP per capita in my economy is simply G that I could call nominal GDP, expenditure, that I could call that is nominal expenditure that somehow is giving me a notion of nominal GDP. I think there is a typo here. There should be a PG, price sub G. Excuse me a second. I guess that all universities are the same. During class time, they should not do this kind of work, but they do it everywhere I went. All right, so there is a PG missing in front of G in this top equation over here. Some of you might have spotted it already. All right, so what is GDP per capita? Well, I take expenditure per capita and divide it by the price. Good. That tells me that I can write GDP per capita as expenditure per capita divided by this object C star. What is C star? The markup. Remember, the firms charge a markup over the cost of production, marginal cost of production. So that's my Lerner index of monopoly power, multiplied by the wage. And remember that the wage is normalized to 1 year. So what is C star? C star is what I call an object that captures the static drivers of the price index. By static, I mean those not related to endogenous technology in the model. And then I multiply by this ratio by z to the theta. What is z to the theta? That's firm level TFP. Then I multiply by n to the key. What is n to the key? Remember, the n is product variety, and what is key is the log of variety parameter. Okay? So I can think of this product as aggregate TFP in this economy. And aggregate TFP in this economy has 2 dimensions. Firm productivity and product variety. Okay. This slide formalizes what I just told you. So I define the operator cap T, TFP. Then TFP growth is the weighted sum of product variety growth and firm productivity growth. In steady state, productivity growth, then TFP growth, then is the weighted sum of 2 terms, the log of variety parameter times the growth rate of product variety. Remember, the growth rate of product variety is constrained by the growth rate of the population. So the first term is key times lambda. That's what I call the Romer component of this theory. Remember, Romer constrained by the fact that there is a fixed operating cost. And then I add what I call the Schumpeter component, which is unconstrained by endowments, which is theta times the growth rate of firm specific knowledge. Again, no scale here. That's the notion of scale invariant that we have here. And notice that lambda can be negative. Okay? That doesn't mean automatically the G star is negative. All right. So now we can play even more with the fact that we have a solution. So I define TFP. Then I define the composite parameter gamma, just to compress the notation. Notice that the composite parameter gamma contains y star divided by n star. So the composite parameter gamma is a parameter that gives information about how pro-growth is this economy. An economy with high gamma is an economy with large firms that invest a lot and grow fast. Okay? So it's a convenient parameter also from the conceptual viewpoint on top of compression notation, because in our mind, we can keep the notion that high gamma means, oh, this is an economy with fundamentals that are conducive to growth. Good. Then I take the log of TFP, and I get the TFP, that at time t, the log of TFP is some initial plus a trend. Remember, G star is the steady state growth rate of TFP. And then I add a term that accounts for the transition dynamics. How did we do endogenous growth in the 90s when I was in graduate school? Only steady states. Lots of people still do endogenous growth studying steady states only. Here we're going to account for the transition. Why? Because we have the explicit solution. So the term accounting for the transition looks complicated. There are 2 parts. This is the transitional part that comes from the deviation of firm growth from its own steady state. That's Z hat. And this term accounts for the deviation of the number of firms per capita from its steady state value. Okay, that I broke down in 2 parts. for convenience. Why? Because if you study carefully this equation, you see that I can approximate both of these logs according to this rule, okay? So that the last three terms of my expression can be compressed into this very single expression, which is parameters times this term over here. What is this term? N star over N0 minus 1. That's the percentage deviation of the number of firms per capita from its steady state at the beginning of time. That's the initial gap in the language of growth regressions, for example. And then I multiply by 1 minus this exponential function of time with the eigenvalue of the system there that captures how TFP evolves over time. Okay, so this is the path of TFP for my economy in equilibrium, starting from initial condition N0 as it converges to N star.
Sorry, so if the starting number of firms is bigger than the steady state, the transition is slower? Is that right?
Actually, if you make this, so the sign, you're saying that the sign of this term over here, the gap, matters?
Yeah.
This is only telling you if you're converging, if TFP is converging to the trend from above or below.
Okay.
That also translates into a statement about the speed of transition, of course. Well, actually, here the speed of transition is constant in the traditional sense because the eigenvalue is constant. Depends on how you measure it.
Okay.
But I'm going to show you exactly what it means.
Thank you.
Your intuition is correct, however. So if the gap is positive, meaning that the initial condition N0 is smaller than the steady state, then TFP is growing over time. That means that I'm converging from below. If N0 is larger than N star, okay, then this term is negative, then TFP is slowing down over time. Maybe that's what you had in mind. That means that we're converging from above. That's a growth acceleration. The previous case is a growth deceleration. The important thing is that this equation is telling you exactly things in terms of growth accelerations, growth decelerations. And I'm going to show you exactly how it works when we do comparative dynamics. All right. Now, the fact that we have a closed form solution for the path of TFP means that we have a closed form solution for welfare. Okay? Because I have that expenditure per capita, consumption per capita. So remember that I have this expression for consumption per capita. So consumption per capita is this term multiplied by TFP. So I substitute that into my welfare function. So I have the welfare at any point in time. This is utility. Then my welfare integral now contains an object that I can evaluate. Why? Because I have that time path of TFP. Remember, the key is this. The TFP, the log of TFP depends on time according to this exponential term. All right? That's how simple it is. You can do this in 2 lines of algebra. Substitute the expression for log of t in this integral, do the integration, and you get the solution. Where, differently from the standard practice, I don't, quote unquote, normalize initial productivity TFP as 0 because I don't want to purge initial productivity from the system because I want to keep reminding myself that initial productivity in fact contributes to welfare, plus initial productivity in some applications that I have in the book, particular trade, is potentially endogenous. Okay, so what's the welfare here? Household welfare is the mass of family members at time 0. Okay, remember this is a Benthamite. I call this the Benthamite effect. This is a household where they all like each other, so definitely not like some Italian families that I know, or families in other parts of the world. And this is the present discounted value of individual utility per individual utility. That has 3 terms. The intercept term, which is the discounted value of what the literature in the 90s identified as the level effect that comes from expenditure per capita, and we have a closed form solution for expenditure per capita, and then this initial productivity. Then we have the term that comes what was known as the growth effect, which has a discount, is discounted the square of the subjective effective discount rate here. That's my G star. And then there is this term that was nowhere to be seen any time in all my time prior to myself and others started working with these models, which is the contribution to welfare of the transitional dynamics. So there is an expression that depends on parameters. I'm going to call this expression over here the welfare multiplier. So what this tells us is that welfare depends on the gap, because the size of the gap is going to tell you how long are you spend on the transition, and the speed of the transition, the steepness, etc., the duration of the transition, then through the parameters of the model translates into a level of TFP that then translates into a level of consumption per capita that then translates into, that then contributes to welfare. So we have a closed form expression for welfare generated by the equilibrium path of this economy. Now, this derivation is for N0 in the endogenous growth region. Okay? If I try to start my economy for a very large N0, very much to the right in the phase diagram, okay, then I need to split my welfare integral in three parts. It can be done, it's just a lot more algebra. Okay? But that's an important thing here. All right, so that's one of the interesting results and the potential for using these things. So let's go to the global dynamics now to do some even more fun stuff. So J equilibrium, there are two possible configurations. There is the free entry, and I think that conceptually you have a good grasp of what's going on here. So we can speed up things a little bit. I told you that there are functions giving me expenditure as a function of the state variable and the interest rate of the function of the state variable in both cases. In the free entry region, these functions are peculiar in the sense that y is just equal to y star, no matter what the state variable is, and the interest rate is always rho. In the other case, I have function. Now, to do the global dynamics, I switch notation. I define X, firm size, which is market size divided by market share. So these are a measure of firm size, which is sales per firm. I keep working with the expenditure per capita. And the change in notation is for two reasons. Number one, it simplifies the derivation of the results enormously. Number two, it's very intuitive to think of this theory as this theory is about firm size. So let's measure firm size directly. Now, firm size is the inverse of the number of firms. Remember that we showed that the number of firms is growing logistically. The beauty is that then firm size is going to follow a linear process. Okay? So remember that I have three regions of state space. So with minimal algebra, I can write the dynamical system, the global dynamical system, with my new state variable as a piecewise linear differential equation. Okay? And because X is the inverse of N, then when I go to the state space, basically everything is flipped over. And I have closed form solutions for analytical solutions for all the thresholds, giving me the partition of the state space. So this is the phase diagram for expressed in this with this new variable. Piecewise linear differential equation. That means that we have the global solution, analytical solution of for any initial condition of this model. And the important thing is that using this variable, the model becomes almost elementary in terms of how it works. So what is the rate of firm growth? Z hat. Well, it's zero when they don't want to invest. And I can write it as the steady state growth rate plus a term that gives me the deviation of firm size from its own steady state. All right? And I think that this is good. This is exactly what Fabio was getting at early on. Okay? If I have a transition where X the initial x is smaller than x star, then this term is negative, and that would be a transition that as x grows, give me that z hat grows. So I have a growth deceleration, with returning to the steady state from below. Strictly speaking, I'm going to argue that and show you that this expression, simply substituting in the analytical solution for x, this is going to give me the impulse response function for z hat when I do experiments changing parameters of the model. Now, the same applies to the gross rate of entry, the net rate of entry and hat. It's a piecewise differential equation that depends only on x. Once I substitute in the analytical solution for x as a function of t, this is basically giving me the impulse response with the temporary deviation and the return to steady state of the growth rate of the mass of firms in this model. This is how simple it is. So this is the analytical solution for the variable x. And again, it's a linear differential equation, so I don't need to say much about this. You guys are all familiar how you play with that. So a word of initial conditions. When you want to do experiments, you have to remember that x is a composite variable. There is y at the numerator, which is a jumping variable. And so you need to recover from your equilibrium equations, the proper expression for the initial condition given the state variables. Okay? So this is the proper initial condition from which you start your system when you start from n0, number of firms, and lambda initial population. All right? So, and then you can play the games that you want. Now, another thing is that, see this explicit solution? There are these dates, Tn and Tz. This is the date at which this economy activates creation of new firms. This is activity that I call entrepreneurship. Then Tz, this is the date at which firms start investing in-house. Okay? And I have analytical solutions for those dates. That's how detailed the information that I can extract from the model. Maurizio and I have a paper where we use this property of models of this class to actually calibrate parameters from using as data moments the date of the industrial revolution and events like that. That's another thing that you can do. This is the visualization of the transition path for my economy. So give me any initial condition, x0 larger than x min. Remember that the system can never be below x min because that's where firms do negative profits, and so somebody acts instantaneously. So give me any initial condition in the range x min infinity, then the system converges to x star. And I drew the picture only in the case of convergence from below, because that's typically what we have in mind when we think about secular growth. But when you do shocks that displace the economy from the steady state, then you can also have convergence from above in this system. And I show you another way to visualize that kind of behavior in this class of models. So these, remember that we know everything here, the model is fully solved. So not only I know the transition path, the analytical solution, this is just the qualitative representation of the analytical solution of the model. Associated to this analytical solution, for firm size, there is the analytical solution for the behavior of expenditure per capita and the interest rate in this model. So prior to the activation of entry, the economy is in the regime where free entry fails, no innovation of any time. Call it that the pre-industrial state, we're going to call it later on. Then expenditure per capita is growing because firms are becoming more profitable as the population grows exogenously. I have a paper where I call this Smithian growth. And so Smithian growth basically creates the conditions for the activation of Schumpeterian growth in this class of models. And in the Smithian phase, the interest rate is always decreasing. All right, so then let me give you an intuition about the engine of growth of this model. We can play with our equations, the return equations, and write them as two relationships with firm investment on the left-hand side and a measure ln over ln of investment in entry. So remember, there are two activities, investment activities in the economy: invest in the growth of an existing firm or create a new firm. And the entire model, the no arbitrage equilibrium, is about determining the allocation of labor to these two activities. And then there is production, et cetera, et cetera. So we can interpret these two functions as representing the profit maximizing or value maximizing investment in firm growth that incumbents want given investment in entry. And the second line describes the investment in firm growth that entrants would like to see given how much investment in entry there is in this economy. Okay? And then there is the state variable X as something that moves this logic around and therefore gives us the transition. So I think it's very useful to think of these as two reaction functions. The top one tells us how incumbents respond to entrants, and the second one tells us how entrants respond to incumbents in this sort of Nash equilibrium interpretation of the no arbitrage argument. And then we can draw a graph like that explains what's under the hood of this model. So initially, both of those two lines are out of the positive quadrant here, meaning that initially market size is so small that incumbents don't want to invest, so they want LZ equal to 0. And entrants say, well, we're happy that they don't invest because we are not investing either. And given our investment decision, 0, we would like them to choose 0 as well. Okay? So that's the way you can think about this. And so initially, the equilibrium of this economy is at the origin of the positive quadrant, the blue dot, in which Nash equilibrium says they agree on the fact that neither group should invest. Then the way the parameterization of the model that we're working with has that entry starts occurring before firm investment. So that's the case in which the line describing the reaction function of the entrance, which is downward sloping, enters the positive quadrant, while the other guys are still at the corner solution. Being at the corner solution means that basically they are on the horizontal axis because they want LZ equal to 0. So the equilibrium moves on the horizontal axis, moving to the right, and that's the red path. Then at some point, the market becomes large enough that the incumbents would like to invest. And then the equilibrium is the intersection of these two lines. See, the incumbent follow this dashed line that now is in positive space. So we start creating a positive intersection that moves to the right and up as market size increases until convergence to the steady state. That's a game theoretic interpretation of the general equilibrium under the hood driving this transition. Okay? And remember the X, the growth of X is generated by these two investment activities that take place jointly. So that's what this part of the model is doing. Okay, now a very useful tool to then play around even more with the model is to write a TFP growth that I'm going to call G as a growth function. TFP growth, in fact, maps into GDP growth. That's why I'm using the letter G to denote. So you can replace TFP with GDP per capita growth here if you want. So I'm going to call this object a growth function, which is growth as a function of the state variable of the model. Now remember, I know the transition of the state variable of the model. I have the analytical solution. So if I substitute in X as a function of time, I get G as a function of time. So I have the solution of the time part of the growth rate in this economy. But for many purposes, it's very useful to have this function, particularly when we do comparative dynamics exercise. And so this is what the function looks like if I have delta positive. Remember what delta is, the death rate of firms. This model allows negative productivity growth over some region of state space when there is no growth, when there is no product variety expansion. I'm not going to use the delta positive case when I want to do secular growth examples because it strains a little bit the interpretation. But when we want to do experiments concerning, for example, a shock to a modern economy, and I will show you some, then delta positive has the property that it can generate a period of negative TFP growth. Now, lots of people have always reacted. In my youth, if you talked about negative TFP growth, people would have told you, well, what are crazy? What did you drink last night? But I'm from a country originally, Italy, where for the last 20 or so years, there has been documented negative TFP growth. According to this theory, that's not a puzzle. This theory generates structurally a period of negative TFP growth when you shock the economy in a particular way. All right? So that's what I wanted to share with you with the first set of slides. We have been gone an hour and a half. If anybody has questions or wants to take a short break, then I will move to the second set of slides where I think I will go faster because we have prepared the ground for interpreting quickly what I want to show you next.
Well, thanks a lot, Pietro.
Yes.
Really great. And I would have one short question. And perhaps, I mean, I'm not sure. For me, it's fine if we go on, but we can have a break as well. So whatever your preferences are. Do you want to have a
going, but if anybody needs a break, nature might be calling. It's fine with me. So while I change the slides, we can take a 5 minutes break.
Perfect.
But if you want to ask the question, I can answer now, or you can ask later.
So it's really a great framework, and I really like it a lot. And one thing that came up when you talked about this transition from Smith to Schumpeter and so on and so forth, there is this kind of theory of unified growth theory of Gala and Weil that is more with human capital and fertility. Do you think of your framework as kind of a complementary framework in the end that explains similar things from different perspectives? Do you think it should be merged, or do you think it's just it doesn't matter as such that they are just focusing on different aspects?
It's a fantastic question. I love it. I get it all the time. And over the years, I decided that the best answer I can give you is that I see my framework as complementary and complementary to UGT. The first part means that says that, and I mean it, that the fact that people bring up UGT in relation to what I'm showing here is a compliment paid by me to Oded and David, the creators of UGT, because it's a fantastic contribution to our understanding of the economy. And in some sense, I take it as a compliment when people say in reaction to my work, oh, but it's related to UGT. Yes, but they were there first. They did a bunch of other things. I don't have human capital in my model. For once, I do have endogenous fertility in a lot of applications, but their theory is really about from Malthus to the modern Schumpeterian era. They downplay the endogenous innovation component, as you know very well in the work that you do. So that's the complement part. We are playing nice here. And then it is complementary, precisely because in their work, they downplay two things. Number one, the Schumpeterian component. And as you know from previous conversations and my own work, they downplay the role of natural resources in the growth process. They basically have only land. But they also downplay the implications of having a natural resource in a model of the ambition of unified growth theory. And in some of the work that I've done, for example, I discovered that if your natural resource is not land, but for example, you put exhaustible resources, then delivering the results of UGT becomes a lot harder. So I see everything I do as complementary to what people in the field do. And as you know it better than me because you have worked a lot more than me on integrating endogenous innovation in that framework. So that's maybe is a long answer, but I think it's a question that is worth asking all the time.
Thanks a lot.
Pietro,
Yes.
I was hoping to ask a question about the explicit ordering between the threshold for N growth and Z.
Yep.
So what is the key feature of the model that delivers that unambiguously?
You basically make a parametric restriction. It's you as the analyst make a choice. When I started working on these things, and the paper that Klaus mentioned earlier, my Smith to Schumpeter paper, published in 2015. In that paper, I actually studied the transition in both cases of orderings of the thresholds. So if you look here, you see that we have explicit solutions for xn and xz. See this?
We can't see your screen, or at least I
Can you
can't.
see my screen? How come?
I can see the screen.
I can see your screen, yeah.
Okay.
Oh, it's just me then.
Yeah, okay. So there are explicit analytical solutions for the two thresholds as a function of the parameters. That means that you basically have a condition of parameters that gives you one ordering and the condition that gives you the other ordering. You can study the transition dynamics in both cases, and I've done in that paper of 2015. But in all applications that I've done later, I decided that the more natural sequence that allows these models to capture what we observed in the historical record is entry first and firm innovation later. In some papers, we talk about the first and second industrial revolution. In much of the work that I'm doing, for example, with Maurizio, with Angus, Chu, and others, we talk about the crossing the threshold XN as the transition from the pre-industrial era to the industrial era. I'll come back to this point later. So those are the kind of arguments that drive the choice to focus on one particular configuration. But the other one can be done. It's a little bit harder algebraically, but it can be done.
Great, thank you.
Sure. Oh, and let me add that in the work that I mentioned earlier with Maurizio, we actually calibrated the two thresholds in a variant of this kind of theory. And so you can use data to give you information about what sequence you want to choose.
If I can add one more question, I'm
Sure.
Fabio. I was curious about the negative TFP growth issue, because the graph seems to suggest that it is related to the size of firms. So I was wondering if you could say a bit more on why it can get negative.
Yes, it's because firms are, there is net exit. Remember the firms die, that's why everything is predicated on delta positive. Firms die at some exogenous rate. So what's happening there is that the gross rate of entry goes below delta. Okay? One analogy that I can give you is that the mass of firms in this model plays a role very similar, almost identical to the role that capital plays in the neoclassical growth model. And how do you shrink a neoclassical economy? The capital stock grows. The gross investment rate is less than the depreciation rate. Same thing is happening here. Why does that translate into negative TFP growth? Because of the law of variety effect.
Yes, I see.
So
So
if I set the parameter key or chi, depending on how you like to pronounce it, equal to, let's go here. So if I set this parameter chi equal to 0, no law of variety, then this channel is dead.
I see. And in that case, would the solution be like lowering the entry barrier? Like lowering the phi? Would that be
Are you asking me how can I generate a transition that is temporally in this region?
Yeah, once you're there, it would be a solution like reduce, like from a policy point of view.
Yes, I'm going to show you a couple in the next set of slides are going to show you exercises where a shock puts the economy in this region. And then the dynamics will take the economy out. I'm going to show you exactly how. That's the beauty of having a model that has the solution.
Thank you.